This is the ninth lecture of the series of lectures under the caption bracket algebra. Let us briefly mention the essentials or the core points of lecture 8. In quantum mechanics, state of a system is represented by state vector, and this state vector is defined in a linear vector space, a complete linear vector space that contains inner products. Such a space is called Hilbert space. Hilbert space allows calculation even in infinite dimensional space. It gives the scope of error-free calculations, and rigorous calculation can be done in this Hilbert space. Another aspect is that the wave function psi of x, which is bra x get psi, should be normalizable to unity, say, and this is expressed through the relation integration from minus infinity to plus infinity psi star of x psi of x dx equal to 1, or the wave function should be normalizable to the Dirac delta function through a relation like integration from minus infinity to plus infinity psi k star of x psi k prime of x dx equal to Dirac delta of k minus k prime. We now discuss the topic of the current video, namely triangle law. We first discuss with respect to vectors. Consider three non-collinear vectors, vector A, vector B and vector C, and they satisfy the relation vector A plus vector B equal to vector C, which is the famous triangle law of vector addition. Suppose they have the orientation as follows. Let me draw the vectors to show the mutual orientation. This is vector A and here goes vector B. This is vector C. The length of vectors are written as follows. The length of vector A is mod of vector A, or simply A. The length of vector B is mod of vector B, or simply B. The length of vector C is mod of vector C, which can equivalently be written as mod of vector A plus vector B, because we have just now written vector A plus vector B equal to vector C. We can also simply write the length of vector C to be simply C. Let us refer to figure, and here it is. From figure, the relation between the lengths is obvious, and let us write it for the case we are considering, that is for three non-collinear vectors, vector A, vector B and vector C. Vector C being equal to vector A plus vector B. The relation is A plus B greater than C. We can rewrite in terms of moduli. So mod of vector A plus mod of vector B is greater than mod of vector A plus vector B. And this relation is referred to as triangle law of inequality. Suppose the vectors are collinear. Let us show the orientation now. This is vector A, this is vector B, and here is vector C. Then how are the lengths related in this case? Clear that A plus B equal to C. Rewriting in terms of moduli, we write mod of vector A plus mod of vector B equal to mod of vector A plus vector B. This relation is the triangle law of equality. Combining the two relations, we end up with A plus B is greater than or equal to C. Written in terms of moduli, we get mod of vector A plus mod of vector B is greater than or equal to mod of vector A plus vector B, since vector C is vector A plus vector B as mentioned previously. This relation is called triangle law. Having completed the discussion with vectors, let us now rediscuss in terms of ket vectors. Consider three kets, ket A, ket B, ket C, and ket A plus ket B equal to ket C, written as ket A plus B. The norm or length of kets are as follows. Norm of ket A is under root bra A ket A. Norm of ket B is under root bra B ket B. Norm of ket C is in fact the norm of ket A plus B, and it is under root bra A plus B ket A plus B. The norm or length of kets are related as follows. Norm of ket A plus norm of ket B is greater than or equal to norm of ket A plus B, and this can be compared to the relation mod of vector A plus mod of vector B is greater than or equal to mod of vector A plus vector B. We can write it more explicitly as follows. Under root bra A ket A plus under root bra B ket B is greater than or equal to under root bra A plus B ket A plus B. And this relation is the triangle law. Let us end with a question that we can discuss in the next lecture, namely, what is Cauchy-Schwarz relation?